How has air pollution influenced levels of rainfall in the U.S.? Hello, friends. Jim here. A study that appeared in the online publication EOS, air pollution has masked climate change's influence on U.S. rainfall. A study suggests that high levels of aerosol pollution have offset higher precipitation levels caused by a warming climate. Greenhouse gas emissions raise the temperature of the atmosphere. Scientists expect global rainfall to increase. And that's because, for every 1 degree C increase in temperature, the atmosphere can hold approximately 7% more moisture, more water vapor. And if it's holding more moisture and water vapor, presumably that leads to potentially more precipitation. So, trying to figure this out as to what the precipitation is going to be is a challenge. And, especially for, farmers, water managers that need this information so they can act accordingly. Especially for rainfall, what's happening locally is really important, said Mark Risser, a climate scientist at Lawrence Berkeley National Laboratory. He is an author of a recent study published in Nature Communications that aimed to clarify rainfall trends in the United States by incorporating data about aerosol air pollution. Now, aerosols are small, very small, floating particles that have they say, a drying effect on global climate. Some sources of aerosols are natural, such as sea spray, volatile organic compounds released by plants, dimethyl sulfide by phytoplankton, also volcanic output. And then the anthropogenic sources such as burning fossil fuels. Now, I want to kind of this notion of a drying effect. Usually to form clouds, which then you accumulate the water vapor, and then it accumulates to the point where it overcomes the natural buoyancy, gravity takes over, and it falls to the surface as precipitation in some form. Usually to form the clouds, you need what's called a hygroscopic particle. Aerosols are perfect for that. Aerosols form just exactly that. They provide a load of hygroscopic particles. So that statement, I'll be honest with you, that statement kind of confuses me. And if you listen to the atmospheric folks who keep pushing that the aerosol is warming the planet and causing sea surface temperature increases, not. What they argue is that less aerosols, because there is this source of hygroscopic particles no longer there, that there's actually fewer clouds. Well, fewer clouds mean less precipitation. That's what they're arguing. So this seems to be almost like contradictory. That's the beauty of science. It kind of teases all out. But what it really comes down to, I'll share that thought in a moment. The research suggested that climate change-driven rainfall increases in the United States have been offset by historically high levels of aerosol pollution. But because aerosol levels have fallen in recent decades, thanks to the Clean Air Act 1970, we're beginning to see more heavy rainfall. Factoring this pollution into climate models can make regional trends clearer. The implication is that aerosols have been disguising the effects of greenhouse gases on rainfall. We unmask changes happening behind the scenes. Well, for reasons that I just explained, it does seem contradictory. Precipitation levels vary highly from year to year. It's extremely challenging to separate the slow changes wrought by global warming from those yearly trends, said Jesse Norris, who studies precipitation at UCal Los Angeles Center for Climate Science. Not involved. As concentrations of greenhouse gases in the atmosphere increase, Earth gets hotter, warmer air can hold more water vapor, and warmer oceans are more prone to evaporation. All true. This should result in more rain. But again, you need the hygroscopic particles for the vapor to coalesce around. And it said right here, what I said earlier, for every degree Celsius increase, there's about a 7% increase in the, I wouldn't say global average precipitation, but more in the water vapor content of the atmosphere. Rizzo said that the complex effects of aerosols have made it more challenging to clearly see how climate change is influencing precipitation. Okay, fair enough statement. The aerosols examined in this study offset the effect of greenhouse gases by reflecting solar energy back out into space and cooling the planet. Okay, no arguments there. But these aerosols can also have localized impacts on precipitation. That's because aerosols can influence what kinds of clouds form and how water droplets form within those clouds. Okay, that's valid. That statement right here is valid. So he's basically acknowledging that aerosols provide the hygroscopic particles for which clouds are needed to form, but then what type of water droplets form within those clouds. Okay, that's perfectly valid. So depending on the season and local conditions, aerosols can also drive the formation of severe storms, as in the case of Hurricane Harvey. What about reduced sulfur dioxide levels and rising rain rates? Aerosol emissions were increasing for most of the 20th century until the Clean Air Act. Main source of SO2 is industrial burning of fossil fuels, particularly at power plants. SO2 emissions contribute to acid rain by mixing with water to form hydrosulfuric acid. And then it falls in lakes and it reduces the pH. Inhaling SO2 can cause respiratory problems, especially a person suffering with asthma. This kind of air pollution can also drive the formation of another form of pollution called particulate matter, which can cause respiratory problems as well as cardiovascular disease, pregnancy complications. So after 1970, SO2, sulfur dioxide, aerosol emissions in the U.S. fell gradually, but in the past 20 years have gone back to pre-industrial levels, said Risser. Norris said it has taken some time for the climate impacts of this to emerge in data because aerosols can persist in the atmosphere for years. The impact of those aerosols not being emitted is becoming clear now. Okay. So the atmosphere folks said that the reduction of aerosols has caused this massive increase in warming. It does have an effect, the aerosol masking effect, but the increase in warming is just because we keep pumping greenhouse gases into the atmosphere. And the ocean's also diffusing heat to the atmosphere. So let's keep that in mind. So Risser and his team used 120-year rainfall records to study both extreme average rainfall trends. They separated these trends by regions and seasons, and then combined these data with the emissions estimates of both greenhouse gases and SO2s. After accounting for the SO2 aerosol and the greenhouse gas emission, Risser said global rainfall trends become more evident. Increasing greenhouse gas levels cause increased average and extreme rainfall across all seasons in the U.S. Study also looked at seasonal emissions precipitation trends, dividing the country into 25-kilometer boxes. That's pretty detailed. Winter and spring, the study found higher local aerosol emissions lead to drier conditions. In summer and fall, the opposite is true. Well, colder temperatures just hold less moisture. Come on. These seasonal trends are clearest in the northeastern and southeastern U.S. and the Great Plain. For western U.S., the study is less conclusive. A lot more year-to-year variation in rainfall in the western U.S. Probably got to factor in ENSO cycles as well. Cornell University Earth and Atmospheric Scientist Natalie Mahowald is more skeptical. She noted that aerosol sources and distributions prior to 1980 are not well known. She said this injects substantial uncertainty into the rainfall study. And he pointed out that many other kinds of aerosols, including nitrogen oxides, black carbon, and those found in wildfire smoke. Adding these into the study could change the results. Exactly. I agree with that. And let's not forget that with climate change, we're also seeing changing patterns in, the jet streams and precipitation patterns. And what's basically happening is that dry regions are becoming drier, wet regions are becoming wetter. And that's because the conditions favor either no clouds forming, making it dry, and therefore they warm up more so. And if there's no clouds, you're not gonna have those hygroscopic particles to form the clouds. But the wet areas are getting wetter because you have the precipitation, then you have the evaporation, you form the clouds, right? And you get more rain. And don't forget what what hurricanes do and typhoons. So to me, I see various contradictions at work here. Hygroscopic particles are needed to form clouds, and then to form significant levels of moisture that can return to Earth as precipitation. But to say that aerosols have actually hindered precipitation levels, I am not convinced. As I said, the aerosols and the different types of them and the different sources of them are needed to form the water droplets that then get returned once they overcome, once gravity can work on it, fall to the planet. So reduction of aerosols should actually lead to less cloud formation. Yes, there may be more heat energy trapped in the atmosphere, and you do need the clouds for that. But even so, you just have an increased long wave radiation that can still be trapped by the atmosphere by interactions with the gases in the atmosphere. So that will lead to a planetary warming. And models that I have seen indicate that the amount of clouds in the atmosphere could actually be on the decrease, and decrease as the planet warms and warms and warms, decrease to such levels that they'll be scarce. I have actually seen some models of that. Can't say I'm convinced on that, but they're there. They're out there. So this is very dynamic. Will there be more clouds or less clouds? Will there be more precipitation or less precipitation as aerosol levels decrease? Well, I've already shared my thoughts on that, but there's more to aerosols than just SO2. There's the nitrous oxides, there's sea salt spray, there's DMS, wildfire, the occasional volcano popping off. They all have to be factored in. And this study, while it may, provide some insight into the role of SO2, I do not consider this to be comprehensive. Just as the atmospheric scientists who don't take into account the oceans. when they look at Earth energy imbalance and warming and so on. They look at short wave in, long wave out, top of the atmosphere, and make a calculation. They're not counting in the heat diffusing from the atmosphere, contributing to EEI. So, this is interesting. You can draw your own thoughts on this. But as I said, the usual concept here is that aerosol particles are needed because they provide the hygroscopic particles for which water vapor can coalesce, eventually becoming heavy enough to sink to the planet. Less aerosols, less hygroscopic particles, less water vapor coalescing to be heavy enough eventually to become precipitation. Granted, a warmer atmosphere holds more water moisture, but you need to be able to coalesce that. And that's the role of hygroscopic particles. So the thinking should be that less aerosols, less hygroscopic particles should lead to a decrease in precipitation. They argue here that is the opposite. I'm not convinced. So, interesting. Needless to say. Until next time.